Hi all, this is my video number 10. Alright, before I give you the example of what we have discussed in the couple of videos, I will give you theorems relating to resolvent and iterated kernel for the non-homogeneous random integral equation. Yeah? Theorem on the resolvent and iterated kernel for non-homogeneous random integral equation. Okay, so first theorem is that the resolvent kernel for the non-homogeneous random integral equation can be written as or satisfies this relation, yeah? R xt lambda is equal to k xt plus lambda ab k xs rst lambda ds, where k is the kernel to the non-homogeneous random integral equation. Yeah. So the resolvent kernel can be written as that. So we prove this from the definition of the resolvent kernel. Definition from the definition of the resolvent kernel, we have R xt lambda is given as summation of m 1 to n 1 to infinity lambda m minus 1 km xt. Yeah, that's the definition of the resolvent kernel, and the iterated kernel is defined as k1 xt as kxt and km xt. This is integrate a to b k xs km minus 1 st dt. Yeah, let me write down the non-homogeneous random integral equation, which is given as ux equal to fx plus lambda ab k xt ut dt. Yeah, this is a non-homogeneous random integral equation. Okay, so from that equation, okay, from the definition of the resolvent kernel, so let me write this as a 1, let me write this as a 2. Okay, just give a name. Okay, so from 1 we can write this as a we can take out one of the k, so we have r xt lambda, this is equal to k1 xt plus sum m equal to 2 to infinity km minus 1 km xt. Okay, we take out k1, so what left now is this summation begin with m equal to 2. Now if we use the definition of the iterated kernel, alright, then we have the resolvent can be written as, so using 3 we have those rxt lambda can be written as k1 kxt, this is kxt, sorry, this one k1. So we have k1 xt, and k1 is equal to kt here. So here is k xt plus summation m equal to 2 to infinity. We have I think I'm missing lambda here. This should be lambda m minus 1. So lambda m minus 1. So km, this is our km. So we have integrate a to b k x s km minus 1 st dt. Okay, now we set that m minus 1 equal to n. So what we have now, r xt lambda, this is equal to k xt plus sum n from 1 to infinity. So we have lambda n there, lambda n. Now integrate a to b k xs kn st dt. And then we can rewrite this. Okay, rewrite that. So we have r xt lambda, this is equal to k xt plus, you can take out one of the lambda, sum. Now I can put m, I can put n, right? So m minus 1 to infinity, we have lambda m minus 1, integrate a to b k xs km st ds. Yeah. So why do we do this? Because we need this this part here to be in the form of the resolvent kernel here, in the form of 1. So we have a definition of resolvent kernel, we have lambda m minus 1. So here we have lambda m minus 1, and inside there we have km, we have km here. So if we change the order of integration and summation here, let me use new paper. Change order of integration and summation. We have our rxt lambda, this is equal to kxt plus lambda sum m equal to 1 to infinity. We have lambda m minus 1. No, I think we should put in, okay, just let me rewrite this thing. Kxt plus lambda, we changed the order of integration, so we have integrate a to b, this summation m 1 to infinity, lambda m minus 1 km st k xs ds. And then we use the definition of the resolvent kernel, this part there, so that we have, this is k, yeah, this is r xt lambda. So here, okay, so we have kxt plus lambda a to b, so we have r s t lambda, so this is s, right, kxs ds, yeah, using the definition of the resolvent kernel. And therefore we can write we can write Rxt lambda is equal to Kxt plus lambda integrate a to b k xs Rst lambda ds. So this is what the theorem wants, right? So the theorem says that for the resolvent kernel can be written as those, so that we have proved that part. Then one more theorem. The iterated kernel, which is kmxt, satisfies we have kmxt, this is equal to a to b kp xy k m minus p y t dy, where p is a positive integer and less than m. Okay, so we prove this. Proof. The definition of the iterated kernel we have k1xt is equal to kxt, and kmxt, this is integrate a to b kx s km minus 1 st ds. Okay, so as we did in the previous videos, we can change the variable, the dummy variable, with s1, and then we can change x so that we can increase, or we can substitute this km minus 1 with a term that we obtain later on. Okay, so if you replace, let me just write s, replace s with s1, so what we have, km xt, this is integrate a to b kx s1 km minus 1 s1 t d s1. And then again we replace m with m minus 1, m minus 1 we replace to m, then s we replace to s2. So what we have k m minus 1 xt, this is equal to integrate a to b x s2 km minus 2 s2 t ds2, from here. For this, we replace s with s1, we have this. Then we replace s with s2 and m with m minus 1. So we have that terms. And then from here, okay, we change x to s1. We change x to s1. So what we have now, that k m minus 1 s1 t, this is equal to a to b, this is k, we have k s1 s2 km minus 2 s2 t ds2. Then we can substitute this. Here we have km minus 1. So in this term here we have km minus 1. So I can substitute this into that equation. Okay, I can give a name here. Let's call this number 1. Let's call this number 2. Then we substitute 2 into 1. Okay. So substitute 2 into 1. We have k mxt is given as, so let me check those things. So we have this is km here, just substitute there. So I can do integrate AB, and then kx s1, ks1 s2, km minus 1 s2 t ds2 ds1. Okay, we just write everything there. Km minus 1 we substitute there. So what left, what we have now is that we integrate a to b we have k x s1 k s1 s2 k m minus 2 s2 t ds2 ds1. So if we proceed this m minus 1 times, yeah, we proceed this with m minus 1 times. So what we have, proceed means we keep on changing km minus 2 here. So the previous one we change, or we substitute km minus 1. Now we substitute km minus 2, and then we substitute, we're going to have terms km minus 3, then we substitute again and again and again. So we end up with km xt is given as a to b, this is m minus 1 times. Okay, and then we have kx s1, k s1 s2, and so on until k sp minus 1 sp for some number p times k sp plus 1, and so on until k s m minus 1 t ds m minus 1 and ds2 ds1. All right, and this is for m. So we can also do for p, kp, yeah, similarly. So we have kp xt, this is integrate a to b, and so on, a to b. This is p minus 1 times. So we have k x u1, k u1 u2, so on, k up minus 1 up, this one kp minus 1 y here, sorry, this is y, then d up minus 1 du2 du1. And we can also write kp m minus p xt this is, we integrate this AB as much as we have P for P minus 1, so M minus P, so M minus P minus 1. So we have M minus P minus 1 times that. So we have this as a K Y V1 K V1 V2 and so on until we have K V M minus P minus 1 T and D VM minus P minus 1 and so on D V2 D V1. Okay, let's call this equation as 1 2 3 2 and this is 3, this is 4. Okay, and then using this 3 and 4, if you multiply this and then we integrate from 0 a to b, so what we have is that, so using 3 and 4, or from 3 and 4, so we have integrate a to b, we have this one kp xt, we have that one k m minus p xt. So xt, so I change that I change that with ky, I change that with y, change that with y, so x, so kx, yeah, y here, there, dy. Okay, that give you integrate a to b, and so on, integrate a to b. So we have k x u1 k u2 u1 from here, u2 u1, okay, and so on up to k up minus 1 y, and we have some more terms there, that, so k y v1 k v1 v2 and so on, k v m minus p minus 1 t, so that d v m minus 1 n minus p minus 1 and so on until you have d v2 d v1, and then we have that, okay, then we have dv1 dv2, then we have dup minus 1 and until dv2 u2 du1, that one. Okay, and then we change the variable again. Okay, change the variable of integration. Okay, change the variable of integration. So what we have is integrate a to b kp xy k m minus p yt dy. This is equal to integrate a to b and so on, a to b. We have k x s1 k s1 s2 and so on, k sp minus 1 SP then K SP plus 1 K SP plus 1 SP plus 2 and so on until we have K SM minus 1 T D SM minus 1 until D S2 D S1. Okay, and then from the previous relation, we have which one here? From here, okay, this is 2, 3, so let me call this, I don't know, 2 already we have, so let's call that star. Okay, alright, so from star, and this is let's call this 1, 2, 3, 4, 5. So then using star and those 5, we have, you need to look at this very, very carefully, because the process of changing from K to K1, K1 to K2 until K M minus 1, K minus 2 up to K P minus 1 P and so on and so forth. The process is just the same. You need to repeat the same process again and again. Okay, so we end up with Km xt, this is equal to 8b Kp xy Km minus p yt dy for p less than m. So that's our proof. Okay, now look at some example. So I think I might discuss 2 examples. If I still have time, I might go another example. Just the quite simple example in this case. Alright, so how to find the iterated kernel? Yeah, find the iterated kernel for the non-homogeneous Fredholm integral equation. For the non-homogeneous Fredholm integral equation with kernel given as kxt as ex cos t, where a from 0 and b is pi. So which means our integral, we have a to b, 0 to pi here. This is in the integration in the Fredholm integral equation. And then number 2, we have k xt is equal to sine x minus 2t for x 0 to 2 pi and t 0 to 2 pi. Okay, I'll do number 1 and then I leave it number 2 as an exercise to you. Solution. So by definition of the iterated kernel, we have what? We have k1 xt is equal to k xt, and kn xt, this is equal to a to b k xs kn minus 1 st ds for n 2, 3 and so on. So with that relation and with that number 1, solution number 1, with that k is given as e to the x cos x, so we have k1 xt, this is k xt, which is e to the x cos t. That's our k. So we have cos t. And then if you use that with n equal to 2, now you have 1, we have 2, we choose n equal to 2, n equal to 2. So what we have, k2 xt a to b k x x. So we have k2 k1 st ds. Okay, so this we have integrate a to b is 0 to pi. So this is 0 to pi. So we integrate 0 to pi kxs. So we have e to the x cos s k1 st, which is also that. So we have e to the s cos t ds. Okay, so I can put that way. And then of course for this you can integrate this, the integration, you can take out the one that free of s. So we have ex cos t, then integrate 0 to pi e to the x e to s cos s ds. Of course here you can use integration by part. Okay, I just leave it that part. So we have k2, just come up with the solution of that. We have negative 1 plus e pi over 2 ex cos t. Yeah, ex cos t, this part is here, and then if you integrate those things, you end up with that. Okay, and then you can also find k3 is given as integrate 0 to pi xs k2 st ds. Okay, if you use that value, this is k. So what we have, 0 to pi kst, which is kxs. So we have e to the x cos s, and k2, so we have negative, we have 1 plus e pi over 2 st es cos t. Is it? Yeah. ds. Okay, and then again you just I think you still got the same. We have you can factor out those, you can bring out those. What left is cos and es. So you have minus 1 plus e pi over 2, all right, ex cos t, integrate 0 to pi es cos s ds. Yeah, if you solve that part, so you're going to have this is minus 1 to squared 1 plus e pi over 2 squared ex cos t. And from this, K1, this is our K1, that this is our K2, this is our K3, and so on. So from there, you can generalize for Kn xt, which is minus 1 n minus 1. We have 1 plus e pi over 2 n minus 1 ex cos t. So that's the answer. So we want to find the iterated kernel. We haven't solved the integrate equation yet, so we will come to that later. I will give that example for solving the non-homogeneous integrate equation. For the time being, just give you how can we obtain the iterated kernel given the kernel in the non-homogeneous Freedom integrate equation. Okay, so that's the first example. For the second example, we're going to find the resolvent kernel for the non-homogeneous Freedom integrate equation. Another example, find the resolvent kernel. Find the resolvent kernel for the non-homogeneous Freedom integrate equation, where our k is given as xt 1 plus x 1 minus t, where a equal to minus 1, b equal to 0. And 2, we have k xt equal to ex plus t for a equal to 0, b equal to 1. So which means the solution for 1, we have, this is for Freedom integrate equation. Freedom integrate equation is ux is equal to fx. Here in this case, fx is not specified, we just specify the k, plus integrate from a to b, so we have minus 1 to 0. Our k is 1 plus x 1 minus t, then ut dt. Okay, that's the Freedom integrate equation. Having obtained k iteratively, then of course you can solve those. So I just leave it to you to solve those things before I discuss that for the particular example. Okay, using iterated kernel, so we have k1, using the iterated kernel. We have k1 xt, this is equal to k xt, this is 1 plus x 1 minus t. And then we can find what k2 xt, which is integrate from I think this is minus 1. Is it minus 1 to, let me check this thing, minus 1 to 0 or minus 1 to 1. Oh, sorry about this. Okay, just a minute. Let me check my notes. Where is it? Can't find that. I think it's minus 1 to 1. And this should be minus 1 to 1. Yeah, so we have minus 1 to 1. So we have minus 1 to 1. Okay, so this, let's continue with that. K2 is given as Kxs K1 st ds. This is equal to integrate minus 1 to 1 1 plus x for kx s. So 1 plus x, 1 minus s, 1 minus s, and then k1 st, k1 st is that we have 1 plus s, 1 plus s, 1 minus t, 1 minus t ds. Okay, so you can take out the terms that free of s. So we have 1 plus x, 1 plus 1 minus t. You can take out those things. 1 plus x, 1 minus t. Then we integrate minus 1 to 1. Here you have 1 minus s, 1 plus s ds. If you do this, you got that the solution is 2 over 3 1 plus x 1 minus t. So that for K2. Then you can do the same for K3 xt. You're going to have 2 over 3 squared 1 plus x 1 minus t, and so on. You can have k n xt as 2 over 3. So you have for 3 you have power 2. For n, so we have n minus 1. Then we have 1 plus x 1 minus t. So therefore we have the resolvent kernel given as, so therefore the resolvent kernel x t lambda, this is equal to, you can use r or you can use tau as well, just the same definition, different symbol. That this is summation of n from 1 to infinity lambda n minus 1 kn xt. Yeah, this is the definition of resolvent kernel. Then this is equal to so we have kn is given as here, all right, and then we have lambda n minus 1. So we can put the lambda n minus 1 there. So altogether you have 1 plus x 1 minus t. This summation should be 1 minus t 2 lambda over 3 n minus 1. And then you can write this as well as this is n from 1 to infinity. So we have 1 plus x 1 minus t summation of those 2 lambda over 3 n minus 1 from 1 to infinity. And this part here as a series, this is equal to 3 over 3 minus 2 lambda. So therefore we have our resolvent kernel is given as x t lambda. This is equal to 3 1 plus x 1 minus t over 3 minus lambda, minus 2 lambda for lambda less than 3 over 2. So all this part here just the algebraic manipulation. You can do those things. All right. For the number 2, that's for the example 1. For the number 2 here, the solution is given as, let me write the solution here. So r xt lambda, this is equal to 2e x plus t over 2 minus lambda e squared minus 1, where lambda less than 2 over e squared minus 1. So this is the solution for the one that I left as an exercise to you. Okay, so I think with those example of how to find the iterated kernel as well as how to find the resolvent kernel, and with 2 theorems at the beginning of the lecture that I gave. So I think I stop here for this video, and we'll meet again in the next video. In the next video I will give another example. Alright, so thank you, bye bye.